Buenos días, profesora Jessica Bloque, vicerrectora de Investigación, Posgrado y Extensión de la Universidad Marítima Internacional de Panamá. Autoridades de la Universidad Marítima que hoy nos acompañan, distinguidos expositores, señores participantes, docentes y estudiantes. Damos inicio a la segunda jornada de el segundo Congreso Científico de la Universidad Marítima Internacional de Panamá. Abordamos el bloque número 7, cuyo tema es ambiente. Nuestro primer expositor es el doctor Makoto Shimamura, de quien me permito leer parte de su hoja de vida. Director General del Centro de Innovación para la Mitigación Meteorológica de Desastres, Instituto Nacional de Investigación de Ciencias de la Tierra y Resiliencia ante Desastres en Ibaraki, Japón. El doctor Makoto es egresado de la Universidad de Tokio como ingeniero ferroviario, donde también obtuvo su maestría en hidrología y prevención de desastres. Profesionalmente, se ha desempeñado como ingeniero ambiental en compañías como Ferrocarriles Nacionales de Japón, Compañía Ferroviaria del Este de Japón, de la cual fue director general, y Ferrocarriles Nacionales Japoneses. Fue científico visitante del Instituto de Tecnología de Massachusetts, también director general del Laboratorio de la Prevención de Desastres de la Compañía Ferrocarriles Nacionales Japoneses y también profesor de proyectos del Departamento de Ingeniería Civil de la Universidad de Tokio. Es miembro de la Asociación Japonesa de Ingenieros Civiles y de la Asociación de Ingenieros de la Compañía de Ferrocarriles Japoneses. Los intereses de investigación del doctor Shimamura se enfocan en la teoría de la probabilidad aplicada, los procesos estocásticos y la toma de decisiones bajo incertidumbre, principalmente en operaciones ferroviarias y mantenimiento de infraestructura. Él observa modelos y herramientas para explorar la optimización, algoritmos para su aplicación en la gestión del flujo en tiempo real de la vía férrea, modelos estadísticos dinámicos para predecir la ocurrencia de varios eventos en tiempo real, como desastres y retrasos debido a terremotos, tormentas y otros fenómenos naturales. Lleva a cabo investigaciones sobre la hidrología de pendientes y el pronóstico de fallas de pendientes, utilizando dispositivos avanzados de medición de precipitaciones y herramientas novedosas como sensores MEMS, análisis de grandes datos e inteligencia artificial. El doctor Shimamura es autor y coautor de 3 libros y más de 70 artículos profesionales. Actualmente se desempeña como editor en jefe del periódico de la Asociación de Ingenieros Civiles de Ferrocarril de Japón, además de su cargo como director general del Centro de Innovación para la Mitigación de los Desastres Meteorológicos en el Instituto Nacional de Investigación para Ciencias de la Tierra y Resiliencia a Desastres en Tsukuba, Japón. El tema a tratar la mañana de hoy por el doctor Shimamura es Stereoscopic Observation of Rainfall Flux in a Basin with Precious Water Resources. Por favor, doctor.
Thank you for the introduction. I'm very honored to be invited to this very important and very interesting for us, the Congress here. I don't understand very much of Spanish language, so I'm not sure that I was not introduced or not. But I'm originally a railway engineer, and I'm very excited to expand my technical view to the world of maritime today. And my name is Makoto Shimamura. So firstly, I'd like to introduce my two co-researcher. One is Dr. Matsuda here. Mr. Usui. Dr. Matsuda is a specialist of earth science in general, especially for the prevention of some accident and disaster due to snow and ice. And Mr. Usui is the president of the company which is specialized with radio communication using the satellite communication technologies. Next, please. Not next, please. And my topic is this, and I mean that a basin with precious water resources is mean, of course, about the basin of Gatsun Lake. It is undoubtedly saying that water resources is very, very important to the operation of Panama Canal. And also Japan is undoubtedly the one of the country which is most heavily dependent, the Japanese industry and Japanese commercial logistics is heavily dependent of the function of Panama Canal. And the water is very, very important resource for entire, not only Panama Canal, and the entire society and economy of Panama. That is overall a reason to choose my topic at this. Next, please. Oh, no.
Right down.
And as written here, the World Meteorological Organization say that among the very various meteorological physical quantities, wind speed and seismic motion and temperature, humidity, among that the rainfall amount is most common for us, but most retarded technology and very uncertain. So they say that developing accurate measurement technology for the precipitation is very urgent task for this field. It is a very big agenda, not only for Panama Canal, but also for earth sciences. Next, please. And we are now doing some project to solve that big agenda. One is a very small trial, but we invented some very special measurement devices, we call the three-dimensional rain gauge. And also, we coming here having some purpose to make a cooperation of observation and research work with your university, UMIP. And also, we are very happy that the UMIP is now, we have now having some agreement to set the site of observation within the vicinity of UMIP campus. Next, please. Now, firstly, I talk a little bit about how to measure the rainfall amount. The rainfall amount, historically, it is very, very elemental devices, which is basically the simple cylinder with opening on top of it. You simply, in old days, we simply measure the depth of water by dipping the ruler on it. For example, at 8 a.m. and 6 p.m. every day. But it is so frustrating measure. We have a now automatic counting device. It's so-called tipping bucket automatic rain gauge. The mechanism of the measurement of that tipping bucket rain gauge is not aperture and the rainfall coming from this aperture to this receptor, and this droplet coming to this one side of the tipping bucket. So collecting the droplet, this side is becoming heavy and heavy. So this tip one side, and count one. And so after the inclinating this side would be here and collect the droplet and count two. This is a mechanism of the so-called tipping rain gauge. There is a very serious flaw, disadvantage of using this type of rain gauge. Next. This type of rain gauge is obvious to everybody. This is good condition to collect the droplets from rainfall. This is practical. This is the condition the rain gauge originally mean. But how about this inclined rain flux toward the horizontal, toward the counter inclination? The rain gauge cannot collect droplet as the amount as it should be. Simply always somewhat underestimate the amount of water. And that kind of disadvantage coming to make not big problem when the water, the rainfall coming in the condition of no strong wind as monsoon season in Japan. But it is very serious problem. One thing is it comes about the condition of the inclination slope. In this picture, in case that rain gauge collect underestimated rainfall, in fact this slope is now very calculating much rainfall than the rain gauge collect. It is sometimes very serious. For example, the slope failure warning system that depending on the amount of water of this rain gauge. This value is not big, but in this slope, the water is very much rainfall. And this is the extreme case. In this case, this rain gauge collect no rainfall in this condition, but still this slope is affected by rainfall. So this is a basic idea to solve that difficulty of counting rainfall and regardless of the direction of the wind in it, the raindrop is containing. This is this case. We want to measure the rainfall amount. All direction of the collecting surface in this horizontal and inclined and vertical or the counter inclinated negative horizontal. So and based on this basic idea, we have developed a very special type of rain gauge, which we call three-dimensional rain gauge, which is this is a collecting droplet collecting part of that rain gauge which is basically composed of 12 receiving cell or chamber, which is basically with two separating walls horizontally, and this vertically one, two, three cones. That is 3 times 4 makes a 12 chamber, and and you see? Oh, okay. Okay. You see this part, and you have already seen that this part, and this is a upright figure of this instrument. The most special part of this mechanism is that this part, aperture, is not only divided into 12 chambers, but also each chamber can count the number of droplets come into each chamber independently and very accurately, using this device based on that each droplet is catched by the electrical cord, and one by one, and the droplet will be 0.1 gram droplet is counted. So the accuracy is very high. Not only high, but also you can know the direction of the flux of the water. Instead that conventional drop tipping bucket rain gauge is only the total amount of rough rainfall amount, only the element of vertical direction. And the completely different problem of doing the meteorological measurement, not only rainfall, but also the wind speed and temperature and humidity, is that how to transmit the data from remote place to your terminal. And it is very often the case you counter. So the typical case is now set here on top of the mountain, but this is not available in the mobile phone communication also, and there's no power supply there. And to solve that problem, this is a system which is this is three-dimensional rain gauge, and this is the data is transmitted to the Inmarsat satellite communication terminal to the in the intermediate center, and via internet directly to your terminal, and also real-time based. Conventionally, this is saying that this is very tedious and costly to not only collect the data, but also to restore the data to the human researcher climbing to the mountain and exchange the memory, but takes it 1 week and 1 month also. So you do not need to doing such tedious work in our case of the system. And also we have completed the analysis and display system that data. Data is complicated, unlike the conventional tipping bucket rain gauge. this is the time series of the total amount of accumulated rainfall, and each time this is a histogram of rainfall intensity. But this is a familiar one. The very special display is this is some three-dimensional, and this is a way from where the rainfall flux is coming, and next period something is like the movement of astronomical bodies like this. So you can understand, this today in the morning the rainfall is coming to very high sky from the east way, but in the afternoon the change, the way coming to the westward, and also the intensity in something blah blah blah. Very, very, very detailed information available, which is sometimes very important in case I got a very good idea to utilize this system for not only the Panama Canal, but also very famous coffee cultivating yard. The coffee or the very some kind of very expensive fruit. There, a farmer is very, very sensitive about not only the amount of water rainfall, but also the direction of the wind of each valley. So each valley has potential of good coffee or not good coffee, and we can analyze in future the nature of this land is analyzed using this device. And also, this is not only completed, but also have several trials to how to make this device reliable as possible. We have doing this test at a special place. So talking about Panama, it's also it's undoubtedly Panama Canal. But you talking about Japan, okay, it's Mount Fuji, right? So Mount Fuji, that one of the very, very extreme meteorological condition. When you can use a device on top of the Mount Fuji, it's okay with everywhere in Japan and also almost a part of on the globe. And we have conducted some weather resistance tests on top of the Mount Fuji. Now this is Mount Fuji on top, and in this top there are some and this is some special buildings, some used to be used by some special measuring devices, measuring center. There's no, this was, now it's no use. And using this condition, we have done the weather resistance successfully, very successfully. And also very various places in Japan. So this is my conclusion about my final target after this present. So doing this kind of test, and not only in Japan but also Panama and the campus of UMIP. And in near future, I would like to complete to make some comprehensive water management system based on this rainfall measurement, very special, very precise rainfall data, and also the meteorological observation system, which calculates the combine and make some deeper insight about the mechanism of the meteorological phenomena about in and outside of the Lake Gatun and also some groundwater condition, the system which analyze and also useful for the forecast about the relations between the precipitation, rainfall, and how delay the time to coming the groundwater come to the surface of Gatun Lake, and the relationship of in and outflow of the precipitation and runoff water, the timing and amount of the water for the Panama Canal. So this is I am very happy we have completed a very, very successful first step of this development in Panama. Thank you very much.